Chen received her bachelor's and master's degree at Nanjing University in China. And then she made a big geographical move to Bonn in Germany, where at the Argelander Institute of Astronomy, she worked with one of the directors, Norbert Langer, which earned her her PhD in early this year. Her next move was geographically somewhat smaller, and she moved, stayed within Germany and moved to Garching near Munich, to the Max Planck Institute for Astrophysics in Garching, which is part of the Astronomy Center in Garching, which also comprises the Max Planck Institute for Extraterrestrial Physics, ESO, two university institutes, and is one of the biggest astronomy centers in the world, perhaps or most certainly the most scientifically diverse one. Chen received there the position of a postdoc, and she's collaborating with one of the directors of the Max Planck Institute, namely Selma de Mink. And Chen's PhD thesis resulted in a paper in Nature Astronomy, and also triggered a press release by the Max Planck Institute for Astrophysics. I think for us, the best aspect of this work is that I think it will also feature in her talk today, which will be entitled, "What can we learn from the multiple main sequence components detected in young star clusters?" And Chen, before you start, let me ask whether it's okay with you that people can ask questions of understanding while you're giving your presentation, and not keep these questions for afterwards.
Well, I think you can just interrupt me whenever you have questions, and I'm okay with that.
Yeah, okay, thank you very much. So please raise your hand. If I don't see you, just unmute yourself. But I would request that we keep all the discussion, not just technical, and not technical or the question of understanding, until after the talk. And Chen, after 40 minutes, I will switch on my camera and show you 5 fingers to signal to you that you have 5 minutes left. And so now the microphone and all screens are all yours. Chen, please use them.
Okay, thank you so much for the introduction, Dietrich. And so I'm really grateful for this opportunity to discuss our work in this group. And I have changed the title a little bit to be more precise. So it is, I want to discuss how binary interaction explains multiple main sequence components in young star clusters. So I will mainly address 2 questions in this talk. The first one is just as a title side, what is the role of binarity in shaping the main sequence morphology in young star clusters? And the second question is in more general, what can we learn about star formation and star evolution by studying young star clusters? So I want to stress 2 things. The first one is young star clusters. We mean the clusters younger than several hundred mega years, and mainly in Magellanic clouds. And the second thing is that here I use multiple main sequence components rather than multiple main sequence populations, as you see in old globular clusters, because the stars in young star clusters are shown to have similar chemical compositions, so they are not in real different generations. So first of all, why we are interested in star clusters? The reason is that all the stars in a star cluster are believed to be born at the same time with the same initial conditions. So the stars can be used to gauge stellar evolution. And this schematic figure shows the distribution of stars in the star cluster in the Hurstburn-Russell diagram or color magnitude diagram. So you can see that more massive stars evolve faster and will leave their main sequences earlier, leaving the main sequence turn off here. So all the stars below the main sequence turn off are uninvolved or less involved stars. If we connect these points, we get the so-called isochrone. And people always use isochrones to derive cluster age. And this figure shows some best fitting isochrones to star clusters. So we can see that the brighter the cluster turn off, the younger the star cluster. But in this age estimation, people always assume that all the stars in a star cluster are single non-rotating stars. Now let's see how recent high precision photometry tells us. So this figure shows the distribution of the main sequence stars in the LMC cluster NGC 1755 in the color magnitude diagram based on Hubble Space Telescope. This cluster is around 60 mega-year, and the right arrow bars on the right side correspond to the photometric arrows at different magnitudes. So we can see different discrete main sequence components that cannot be characterized by one simple isochrone. We see some right main sequence stars, which is the major main sequence containing the majority of stars, and we see a population of blue main sequence stars, including some blue stragglers that are brighter and bluer than the main sequence turn-off stars. And we see right extension on top of the right main sequence. They are probably unresolved binaries because Hubble Space Telescope cannot resolve the two-star components in a binary system. So a binary looks like a single point. And we just need to combine the fluxes of the two stars. And we see that the cluster main sequence turn-off region is extended. So all these features challenge our traditional view on star clusters. As I said, people in the traditional view, people always make a simple assumption that the stars are single stars. But in reality, people have found that most of the stars have close companions, which can be seen in this pie chart. Only 30% of the stars are born like single stars. The others are binaries and will produce different evolutionary products. And this figure also shows the period distribution of the binaries. So you can see that binaries favor short periods. And binary evolution can change the properties of both stars and produce some exotic objects or phenomena. For example, X-ray binaries, some Wolf-Rayet stars, some peculiar supernova, and gravitational waves. So here I want to point out that Schneider et al. Proposed that binary mergers may create magnetic fields on massive stars. This is very important to explain the magnetic fields detected in 10% of the upper main sequence stars, because in those massive stars, dynamo process doesn't work. So this figure shows a previous study on how binary evolution shapes the main sequence morphology in star clusters. And the binary models are computed by the rapid stellar evolution code. So this figure shows the distribution of the binary models in the color magnitude diagram. You can see that the binaries are mainly divided into two groups. The green dots correspond to pre-interaction binaries. And as I said, they are just unresolved binaries, so they locate on the right side. The dark and blue isochrones are just the isochrone of single stars at 1.3 gigayear and 1 gigayear. And the second group is these red stars. They are post-interaction binaries, including binary mergers and stable mass transfer products. So they appear bluer and younger than the other stars because of mass accretion and rejuvenation. So 2 years ago, we built some new detailed binary models with Mesa code. And the advantage of these detailed binary models is that the spun up accretors, the structure of the spun up accretors can be solved in a more reliable way. So we can evolve the two stars simultaneously with Mesa code. And we adopt a self-regulated mass transfer efficiency rather than a constant mass transfer efficiency. That means we know that the accretor will spin up during the mass and angular momentum transfer. We assume that as soon as the accretor reaches critical rotation, no further accretion is allowed. And we assume that the excess material will be removed by the radiation pressure of the two stars. And if the radiation pressure of the two stars is not sufficient to remove the excess material, then we assume the two stars will merge to be a single star. And these figures show the time evolution of our detailed binary models in the Hertzsprung-Russell diagram. So since this is Hertzsprung-Russell diagram, we only show one star in each binary system because we cannot combine the fluxes in Hertzsprung-Russell diagram. And we only show the visually brighter star in each binary system because it dominates the light. And we divided stars into 4 different groups. Blue corresponds to pre or non-interacting binaries, and yellow corresponds to main sequence mergers, and red corresponds to post-mass transfer systems. Green corresponds to semi-detached systems. So we see at 2 megayear, most of the systems are pre or non-interacting binaries, and this curve just resembles the single star isochrone, but we can already see some semi-detached systems and main sequence merger products at this young age. And as time passes by, we see more and more binaries start to interact and produce this extended main sequence turn-off feature. So at this 10 megayear, we see mainly 3 features. This is just the single star isochrone, and we see a discrete right binary feature. I can tell you that these are the accretors that have experienced a successful case-B mass transfer, during which the accretors reaches critical rotation. So these stars are cooler than the other stars only because they have extremely fast rotation. And here is the turn-off binary feature, and it includes the main sequence mergers and post-Case-A mass transfer systems and some semi-detached systems. They appear bluer and younger because of mass accretion and rejuvenation. I will explain more about the difference between Case-A and Case-B mass transfer later with some evolutionary examples. So here I just want to stress rejuvenation. So you can see this cartoon, assuming that 2 20 solar mass stars merge at 5 megayear. At this age, the 2 stars have 50% of hydrogen left in the core. And the merger product is a 40 solar mass single star. And we find that the merger product has 66% of hydrogen after it settles back to thermal equilibrium. So the single star appears like a 2 megayear single star. So rejuvenation means a star appears younger than it really is because its real age is still 5 megayear. And this rejuvenation comes from 2 aspects. The first one is the mixing of hydrogen into the stellar core. And the second one is just the main sequence lifetime of this massive merger product is smaller than its progenitors. So next, I will show you 3 evolutionary examples, 1 Case-A mass transfer, 1 Case-B mass transfer, and 1 main sequence merger product. The left figure shows the evolution of the primary and secondary star in the Hertzsprung-Russell diagram. So this binary contains the 16 solar mass primary star and the 13 solar mass secondary star in an orbit of 2.5 days. And green corresponds to the evolution of the primary star, and blue line corresponds to the evolution of the secondary star. The red panel corresponds to the zoom-in area of the zoom-in image of the main sequence turn-off area or main sequence area. And I plot 3 isochrones at 8 megayear, 12 megayear, and 15 megayear. So the field circles corresponds to the position of the 2 star models at corresponding ages. For example, at 8 megayear, the system is a pre-interaction binary. So the 2 field circles just locate on the right isochrone, and mass transfer happens before 12 megayear. So we see at 12 mega-year, the secondary star appears hotter and younger than this 12 mega-year isochrone because it creates some mass, and due to rejuvenation, it is hotter. But the primary star appears much cooler than this isochrone because of the mass loss. And at 15 mega-year, the primary star has died, leaving the secondary star in isolation. And we see that this secondary star, or the accretor, appears much younger and bluer than 15 mega-year isochrone. So KC mass transfer can produce blue stars or blue stragglers in star clusters if it is massive enough. Now let's see KSB mass transfer. So again, the primary and secondary star masses are the same, but the period is slightly larger. And we see mass transfer happens between 12 mega-year and 15 mega-year. So we can see after the mass transfer, the secondary star model appears brighter and cooler than the model before mass transfer. So the difference between KZ and KSB mass transfer is that in KSB mass transfer systems, the orbit is wide enough to avoid tidal spin down. So the accretor will reach critical rotation by accreting less than 1 solar mass. So it will not experience a strong rejuvenation. But in KSA mass transfer, the accretor can be spun down by tides, so it can accrete more mass and have more rejuvenation, so it can appear bluer than the other stars. So KSB mass transfer produces right critically rotating stars, and we find that all our KSB mass transfer systems will produce one BE star. And now what about main sequence mergers? So we see that the two stars merge at these gray triangles to be a single star model here. And then we follow the evolution of this merger product till the end of its evolution. So the merger happens at 10 mega-year. So we see at 12 mega-year, the merger product appears much younger than this 12 mega-year isochrone. So main sequence mergers produce blue stragglers in young star clusters. But here we make an assumption that the merger products have slow rotation according to Schneider's work. Maybe you are not satisfied with this assumption, but yeah, this is our assumption. And Schneider et al. Also proposed that these merger products may have strong magnetic fields. Then I use a movie to show you the evolution of our detailed binary models as a function of time. Again, in the Hesperron-Russell diagram, but this time color corresponds to the velocity, surface velocity of the star models. And these open markers correspond to the three evolutionary examples I just shown. I will show you this movie. So you can see that this is a clear single star isochrone, and you can see binary evolutionary products. You see a very clear right sequence here. It is the BE star sequence. They have near critical rotation, and you see that binary evolution can produce these blue stragglers. Now we need to compare our detailed binary models with the observations. And this time I use an SMC cluster NGC330 because it is in SMC, and our models also have SMC metallicity to avoid the strong stellar wind. And this cluster has an age of 30 to 40 mega-years. And what's important is that we have the BE star information in this cluster, which is shown by these white dots. So these stars are probably BE stars because they have brightness excess in a narrow H-alpha band. So they are from photometry. And we see that our binary models can reproduce these rapidly rotating BE stars. And maybe this major right main sequence can just be explained by this single star isochrone, and we can also reproduce some blue stragglers in this star cluster. But the problem is that we cannot reproduce the blue main sequence stars. Even though the blue main sequence is not as clear, it's not so clear in this cluster as in NGC 1755, but we still see many blue main sequence stars, and our detailed binary models cannot explain these binary models. So let's see some previous explanations on the split main sequences. It has been widely accepted that the right and blue main sequences are caused by a bimodal rotation distribution, with the right main sequence containing fast rotators and the blue main sequence containing slow rotators. It can be seen in this figure that the right and blue main sequences can be fitted well by the isochrones of single stars that have initial velocities of 65% of critical velocities and 35% of critical velocities. And we see that these right extension stars are confined very well by this equal mass binary line, which may further support that these are just unresolved binaries. So this idea, the bimodal rotation velocity distribution, is supported by spectroscopic measurements of the blue and right main sequence stars in young star clusters, which can be seen in these two plots. So the left plots show the spectroscopic measurements of the velocity of the blue and right main sequence stars in NGC 1818, which is a 40 megayear star cluster. So we can see that the average velocity of the right main sequence stars is larger than that of the blue main sequence stars. And this is the observation in NGC 1850, which is a 100 megayear cluster. Again, the right steps correspond to the velocity of the right main sequence stars, and the blue steps is the blue main sequence stars. So we see right main sequence stars rotate faster than the blue main sequence stars. So what's interesting is that this kind of bimodal rotation velocity was also found in the spectroscopic observation of more than 300 B-type stars in VFT flame survey in 30 Dorados region. So you can just see this right line. This is the best fitting of the observed velocity. So we see two peaks here, and people observe this bimodal rotation velocity distribution, but don't know the origin of this distribution. Some people say that maybe stars are born with slow rotation and binary evolution produces these fast rotators, but I don't like this kind of explanation because there are many fast rotators here, and 30 Dorados region is a very young region, so binary evolution should not play such an important role. So I would rather say that stars are born with fast rotation, and due to some reason, there are some slow rotators formed. So in order to check whether the fast rotators and slow rotators have the same origin mechanism, we check their mass functions. So in order to get their mass functions, we first need to do the isochrone fit. And we can derive the mass of each star according to this isochrone fit. And I show the cumulative number distribution as a function of mass for the right main sequence stars and blue main sequence stars in the left figures with the solid color lines. And we used a power law function to fit the observed distribution. The best fittings are shown by the dotted color lines. The shaded areas correspond to 1 sigma arrow. So what we obtain is that the right main sequence stars seem to follow the Salpeter. I'm sorry, I forgot to say that the black dashed lines correspond to the distribution of the Salpeter initial mass function with an exponent of minus 2.35. So we see the right main sequence stars follow the Salpeter mass function very well, but the slope of the mass function of the blue main sequence stars is much shallower. So it is only -1. So the blue main sequence stars follow a flight mass function. Now, combining what we have learned for these blue main sequence stars, that they have slow rotation and they have flight mass function, and the fact that binary mergers may produce slowly rotating stars, we propose that maybe all the blue main sequence stars originate from binary mergers. And in fact, if all of the blue main sequence stars originate from binary mergers, this flight mass function agrees with the fact that binary fraction increases with stellar mass, and agrees with the fact that binaries with higher masses are easier to merge. So if the blue main sequence stars originate from binary mergers, we can estimate the potential merger time for each blue main sequence star. So this figure is quite complicated, I think, because I always see many confused faces when I show this figure. So the thin solid lines in this figure shows the position of the merger products that are created at different times. For example, let's just see this blue line. So this blue line shows the position of the mergers that are produced at 0 megayear, the beginning of the cluster. And after their formation, they have to evolve another 60 megayear to reach the cluster age. But this brown line corresponds to the position of the merger products that were created very recently at 58 megayear. So these stars appear very blue because of strong rejuvenation. So we can use these merger isochrones to estimate the potential merger time for each blue main sequence star, and then we can do the integration and get the merger history of the blue main sequence stars in this cluster. So the result is shown in this right figure. The x-axis is the potential merger time, and the y-axis is the number of mergers per megayear. So we see merger events peak within the first 2 megayears and then prevalent for tens of megayears. So this early merger rate peak cannot be explained by classical binary evolution because stars do not have time to evolve at such a young age. So we propose that maybe these mergers are caused by strong orbit decay due to dynamical processes, mainly from two types. So the first one is the interaction of binaries with circumbinary disk or ambient gas. And the second one is the interaction between a binary system and a distant third body through Kozai-Lidov cycles. And actually, we have some evidence for this kind of orbit decay. The first one is that recent binary formation models indeed predict that 30% of B-type stars will merge during their early time, either during the pre-main sequence evolution or the first several megayears of their main sequence evolution. And the second one is that Zana et al. Found a flight period, a flight log period distribution in a young star forming region. And if you remember that I have mentioned early in my talk that massive binaries favor short period. So we need a strong orbit decay to explain a large fraction of the short period binaries. And the third evidence is that there's a rapid rise of the velocity distribution with cluster age. The velocity dispersion is a probe of the fraction of closed binaries, because in closed binaries, we expect a large velocity dispersion. So in the left figure, you can see the measured velocity distribution as a function of cluster age. We see a positive relation here. And the right figure shows what is the minimum orbital period that is required to explain the measured velocity dispersion. For example, in this cluster M17, we need a large minimum orbit period to explain the low measured velocity dispersion. So it is several thousand days. But in this cluster, I see 1805, we only need 1.4 days to explain the measured high velocity dispersion. So the right figure means that it will only take around 2 mega years for a binary system to shrink from several thousand days to 1.4 days. So this agrees with our early merger rate peak. So based on all I have said, we come to an exciting conclusion that we propose that stars may be born with two different types. On the one hand, most of the stars are born as fast rotators, and they are just normal main sequence stars. They don't have a strong magnetic fields, and they just follow subheater mass function, and these stars populate the right main sequence. And meanwhile, a significant number of the thus created stars merge in a very early time and produce slowly rotating stars. And these slowly rotating stars may have strong magnetic fields, and they have a flight mass function. And these stars populate the blue main sequence. So this is so this answers my second question: what can we learn about stellar formation by studying the stars in young star clusters? And the first question: what is the role of binarity? So our previous binary models almost have slow rotation because we assume that they are initially synchronized. And as I said, we need fast rotating stars to explain the right main sequence. So we built new binary models in which the two star components all have fast rotation, and then we can compare our detailed binary models with the observations in the color magnitude diagram. So this is a comparison. All the open markers correspond to our detailed binary models, and different markers correspond to different populations. For example, circles mean main sequence plus main sequence stars, and these diamonds correspond to main sequence mergers. Color corresponds to the velocity of the stars. So we can see this time we can reproduce these right extension stars. We can reproduce these BE stars. So the field circles or the dots are the observations. The blue, the black corresponds to normal main sequence stars, and purple dots correspond to the observed HR5 emitters. And we see that our main sequence mergers can explain the observed blue stragglers here, but again, our detailed binary models cannot explain the faint blue main sequence stars because we propose that they come from dynamical evolution, which is not included in our detailed binary models. So in summary, we find that binary evolution can produce spun up stars, these BE stars in young star clusters, and binary evolutionary induced mergers may explain these blue stragglers, these brightest stars. And binary orbit decay induced mergers may be responsible for the faint blue main sequence stars in young star clusters. So this is the first question I mentioned in this talk. So this is the main part of my talk. Now I want to say something about the BE stars in young star clusters, because I know that BE stars are the favorite objects in this group. But there are still many open questions that we cannot answer yet. So we can have a discussion. So I show you the color magnitude diagram of 3 young star clusters. And the right dots correspond to the possible BE stars. So we see some common features. The first feature is that all the BE stars locate on the upper right side of the cluster main sequence turn off, regardless of the cluster age. And all of them extend to 2 to 3 magnitudes below the cluster turn off, again, regardless of cluster ages. And another common feature that cannot be seen directly in these figures, but I can tell you, is that the fraction of the BE stars is quite high near the main sequence turn off. It is around, it is larger than 50%. but the BE star fraction decreases with increasing magnitudes. So this is also a common feature in different clusters. But we also see some differences. For example, in NGC 330, we see a discrete BE sequence here. We see a clear gap between the normal stars and the BE stars. But in other two star clusters, it seems that the BE stars mix with the other main sequence turnoff stars. But we still see many right BE stars. I think we may get some information about BE star formation by studying the BE stars in young star clusters. We know that the BE stars can form either through single star channel or binary channel. And in the single star channel, we know that stars can spin up during a sequence evolution, which can be seen in this left figure. You can just see the right line. So the star can reach near critical rotation at the end of its main sequence evolution. And Ben Hastings tried to use single star channel to explain the BE stars in young star clusters. In the right panel, the black histograms show the BE star fraction as a function of magnitude in NGC 330. Here is the cluster turn off, and the lines with different colors correspond to the predicted BE star fraction as a function of magnitude based on different velocity thresholds for the BE stars. For example, blue means if all of the star models rotate faster than 70% of the critical velocities are BE stars, how many BE stars can we produce? So we can see that single star channel can only explain the high BE star fraction near the cluster turn off, because as I said, single star channel can only produce BE stars near the end of its main sequence evolution. So for these faint BE stars, we need binaries. And yeah, you have seen this figure. You can see that our detailed binary models seem to reproduce the BE star range, magnitude range quite well, but I can tell you that we cannot explain the observations qualitatively because we only predict less than 10% of the 10% of the stars to be BE stars in our models, because most of the case-B mass transfer systems merge due to our criterion. And Hastings et al. Try to relax this criterion and assume that what if all of the binaries can survive case-B mass transfer and produce one BE star? How many BE stars can we get? So this is the result. So you can see the black and orange lines correspond to the predicted BE star fraction as a function of mass to the turn-off mass. So you can treat this as magnitude, and these are the observed BE star fraction. So if all of the binaries can produce one BE star, then we can get at most 30% of BE stars near the cluster turn-off. Then the BE star fraction decreases with increasing magnitude. It seems that the binary channel can explain the observations, even though 30% is still slightly lower than 40 to 50% of the observed BE star fraction. Now let's see some spectroscopic observations of the cluster BE stars. Currently, these kind of observations are still sparse, but we have high quality observations in two star clusters. The first one is in NGC 330. So the left figures show the velocity distribution for the normal B-type stars and the BE stars in this cluster. And this figure shows the velocity for each star in the color magnitude diagram. So these are the BE stars in NGC 330. We can see that in general, BE stars rotate faster than normal B-type stars in this cluster. And in NGC 1850, the gray dots correspond to normal main sequence stars and red dots correspond to BE stars. And what's interesting is that these green diamonds correspond to the shell stars, the BE stars that are observed near the edge on. We see that all these shell stars are brighter than the other cluster members. And the lower panel shows the cumulative velocity distribution for the main sequence turn-off stars, the BE stars and shell stars, as a function of the velocity. So we see again that the BE stars and shell stars rotate faster than the normal main sequence turn-off stars in this cluster. And yeah, due to the effect of inclination, the BE stars have a lower velocity end than the shell stars. But what I don't understand is that all these very right stars in NGC 1850 are shell stars according to Sparskin's work. But Julia told me that not all the right BE stars in NGC 330 are edge-on stars. So I don't know what is the reason for the different distribution of these BE stars in young star clusters. So I think there are still a lot of things we can learn from these BE stars. And that's all what I want to talk today. And yeah, now I welcome questions from you.
Yeah, thank you very much, Chen.
Thank you.
For a very interesting, thought-inspiring talk. And so I invite questions.
Dietrich, I don't know if you can you see the hands or not?
I don't see you on.
Okay, Mark, can you make Dietrich co-host so we can see the hands and run the chat? I'll tell you to start. I think
I saw Yael's hand, so.
Yeah, but Connie and Gloria were before me, I think.
Yeah.
Okay, good. I now see Connie and Gloria as well. So if Gloria was first, please go ahead.
Hi, Chen. This was a really wonderful talk, a wonderful overview. And so it's, as Dietrich said, very thought-inspiring. And the first thought that came to my mind is that to what degree do all your model results depend on the assumption of synchronous rotation in binaries? So if you have synchronous rotation, you know, the stars in equilibrium, and indeed the principal interaction will be when you get to a Roche-Loeb overflow situation. But if you're in an asynchronous binary system, for example, like all the eccentric ones, you have different effects that enter. And so these may alter to a certain extent your results. So I'm just wondering, have you given any thought to this problem?
Yeah, this is a good point. Actually, at this moment, we only consider circular orbits, and we have never think about the eccentricity. I think we need to do that further. But just from my point of view, something is robust regardless of this eccentricity. How should I? Okay. So these are our models. I think the production of these BE stars do not depend on this assumption. It doesn't depend on whether the orbit is circular or not, because the equator will spin up anyway. And also the blue stragglers, they come from main sequence mergers. So I also think those stars will not be affected by this assumption. But I think this kind of assumption will affect the fraction of each population predicted by our models. I don't have a good answer to that question. I think we need to think more about it.
Yes, thank you. But and that indeed, your talk raises a lot of questions which are very interesting to discuss. Thank you again.
Sure. I think we raise more questions than we solve.
So is it then okay if I call up Yael as the next person to ask a question?
Connie was before me, I think.
Yeah, okay, Connie then.
Okay,
Please
can
go
you
ahead.
hear me? Yeah. Thank you, Chen, for a very interesting talk and great work. I have one particular question on galactic open clusters, actually, because for the moment, most of your work is being done at low metallicity. And so whether people like it or not, for the B-star regime, in galactic metallicities, these stars have oscillations, which is, of course, what I like a lot. And we have also evidence that there is more internal mixing, so heavier core masses. And this also shifts your stars in a diversity of places. So I wonder if you have tested your theory on galactic clusters and whether that would provide the need to have different main sequences of the single stars. I'm talking about the single stars, which you will certainly still also have in these clusters.
Okay, thank you for the question. So at this moment, we focus on low metallicity because we want to avoid the effect of strong stellar wind and focus on binaries, binary evolution. And the other thing is that this kind of multiple main sequence morphology is not very clear in galactic open clusters because the clusters are not massive enough. So we see some clusters show this kind of split main sequence, extended main sequence turnoff and BE stars, but they are not very clear enough because there are only few stars, few massive stars in those clusters. That is the problem. But from the theoretical side, of course, I think physics are the same. It's just that at high metallicity, strong stellar winds plays a major role. And the other thing is that we cannot predict the position of the BE stars in the color magnitudes diagram because we did not take into account the contribution from the star disks. And we don't know the contribution from the disks. So I don't think we can predict the position of the BE stars.
Yeah, but I'm not talking about BE stars, which also pulsate, by the way, many of them do. But the point is that that's exactly what we see. And what we would need to have in high metallicity open clusters, there would not be clean sequences. It would be a whole region. So because the different core masses are obvious, I can send you a reference. So it's actually very interesting that we do not want to see multiple main sequences there, but there is still a whole region that you could map out with your theory, I think.
Are you talking about young open clusters?
Yeah, with B stars, and okay, they have winds. Of course, they have winds. We know that, but they are not very strong yet. If we look at like mid-B type stars. Okay.
Yeah. Okay. Good.
Anyway, thank you very much. I have to rush off, unfortunately, but I really love this work. That's all I wanted to say.
Connie, before you disappear very quickly in a rush, I think we all congratulate you very cordially on the receipt of the Kavli Prize. This is very impressive. Very nice.
Thank you.
Congratulations.
I very much appreciate that. And I wish I could be more with this crowd, but my life is a bit busy sometimes.
Please call again in the future. Thank you.
Yes. Bye.
So then, bye-bye, Connie. The next hand that I then see is that of Joe Puls.
Oh, that's Yael.
Okay, so this time I may go, if you let me, Dietrich.
Yeah, sure, please.
Okay. Following on what Connie just said, I can send you a reference also on, we worked on a cluster which has this double sequence, slow and fast rotator in the galaxy. But anyway, I had two questions actually. So one is about, again, galactic objects. So the magnetic stars in the galaxy, could you test if they follow your double sequence? Because you expect them to be in the merger thing, so the second in sequence. So that was my first question. And the second one is, so if I follow you correctly, since you have part of the interaction doing the second main sequence, you have not that many BE stars. And now in Asyncs, it considers that you have all going into the BE stars and you don't go into making the double main sequence. But then you cannot have both ways, right? Either you form the B star or you get this double main sequence. But so there is something.
No, so the BE stars come from. So the BE stars come from successful KSB mass transfer, but the main sequence, but the murders, I mean main sequence murders, so they are KSA mass transfer. So they do not either go this way or that way. So if a star merged during KSB mass transfer, then it will form a post-main sequence star, which is not included in this picture at all. So this is the problem. But if the main sequence merger products have fast rotation, then maybe some of the main sequence mergers can be BE stars. Then we will get fewer blue stragglers and more BE stars.
And what about the galactic magnetic massive stars?
I don't know too much about the observations. I don't know whether the galactic magnetic stars are blue main sequence stars or other kind of stars. So I think I need to learn more about that. I don't know any observations that show that these blue main sequence stars have strong magnetic fields, but this is an observational signature that we predict from our theory.
Okay.
And another thing is that there are around 20% to 30% of blue main sequence stars, but people only observe 10% of the massive stars to have magnetic fields. So maybe there's a magnetic fields decay, or maybe not all murders can create magnetic fields. We don't know that.
Okay, thanks a lot.
Yeah, I don't know whether people can measure the magnetic fields for these blue main sequence stars.
Oh, not in the Magellan clouds. No, no. You can have some evidence, indirect evidence of magnetic activity, but direct evidence, we tried several times and it's a little bit difficult, I would say.
Okay.
Mass object and hot object, so not with current instrumentation.
Okay, thank you so much.
Okay, Joachim Pult, please.
Yeah, actually, my question was already answered because I wanted to ask about the fraction of these blue main sequence stars compared blue main sequence stars compared to the rest, and you said it's on the order of 20 to 30%. Yes, so this is somewhat also incompatible to this 10%, which is an upper limit, I guess. And there might be still, in my opinion at least, might be still the scenario that we have also a couple of stars where we have fossil fields. That's a different story, of course. Good, but thank you. That was a very nice talk.
Okay, thank you.
Are there any further questions? While people are perhaps still thinking about one, let me ask one myself, or this is first a comment. The BE stars are the only B-type stars, as far as I know, in which no large-scale dipole magnetic fields have been detected. So that is a circumstantial evidence in support of what you said, that the red stars do not have magnetic fields, or should not. You do not expect this. Now, as far as I understand it, one of the prototypical stars, which are candidates for a magnetic field that was induced by a merger, is Taos-Co.
Yeah.
But Taos-Co has a very atypical magnetic field. It's not a dipole field. It is very tangled.
Yeah.
And so is that something that gives you problems? And could it, for instance, be that one has Taos-Co-like magnetic fields in BE stars, which are even more tangled and therefore not detectable with current observational techniques?
And let me add that Taos-Co is most presumably a very slow rotator.
Yeah. But that is consistent with the merger hypothesis, isn't it?
Yes.
Yeah.
Okay. Since I don't see any further hands, I would give the word back to Carol to close the session. Thank you all for attending and participating in the discussion.
Thank you very much, Dietrich. I appreciate you introducing the speaker and helping out with the questions. Shane, that was a really interesting talk. Thank you very, very much. And Yale will be hosting these seminars going forward, as I am now the past chair of the working group. So thank you to everyone for all of your stimulating conversations. I have greatly enjoyed all these seminars, that we started during the pandemic. I found them very useful, very inspiring, and very interesting. So thanks to everyone. We have a speaker lined up in January, and Yale has suggested that she might wish to change the format of these, and that's perfectly fine. Whatever the new executive committee wishes, I'm here to help. And thank you to everyone for all your positive support. Have a great day.
Okay.
Thanks, Carol, for everything.
Thank you, Chen. Thanks, Carol.
You're welcome.
Thanks, everyone. Bye.
Thanks,
Bye-bye.
Dietrich.